Swayam Prabha. Digital India. Educated India.
What we will do is before writing down the 3D form of Newton's law of viscosity, we will discuss the one dimensional form of Newton's law of viscosity, so that you can easily understand the 3D form. Okay. What we consider for the 1D form of Newton's law of viscosity is the flow between two parallel plates, which I come across several times. The bottom plate is fixed, okay. The top plate is set in motion at a constant velocity, okay. And now we require a constant force. You are keeping the bottom plate and then top plate is set in motion, which means some force is required to keep this plate in motion. Now, this force required to keep the top plate in motion is experimentally found, note down the word experimentally found, to be proportional to the area. Obviously, larger the area, more force is required, and then it is also found to be proportional to the velocity. If you want to move the plate at a higher velocity, more force is required, and this force is found to be inversely proportional to the distance between the plates. So, smaller the distance, then you require larger the force is required. So, this force is inversely proportional to the distance between the plates, and that is what is expressed by this equation: force proportional to area. So, area has been brought to the left hand side, force per area is proportional to the velocity. So, Vp is on the numerator, inversely proportional to the distance between the plates. The distance between the plate is h, and that is in the denominator, and what is the proportionality constant is viscosity. It is a material property of the fluid, okay. The constant of proportionality is a property of the fluid defined to be the viscosity. So, how do you write little more formally? This F by A is the stress. Because it is tangential force, it is shear stress. Because the force acts along the x direction on a plane whose normal is y axis, it is tau y x, and Vp by h is the velocity gradient. So, we write as dVx by dy, and of course, viscosity. How do you write little more generally? The shear strain rate is given by this expression, which I have seen already, dou Vy by dou x plus dou Vx by dou y. So, what we have is one of the terms, because there is no y component of velocity, only this term alone appears here, okay. So, if you want to write this more generally, tau x is equal to mu into gamma dot y x. That is for the case of fluids, and this for the case of solids, and that is what we have seen in the previous slide as tau x y is equal to mu into gamma dot x y, okay. So, what we have seen is in fact a one dimensional form of Newton's law of viscosity. Here it is x y and here is x y, and here we have written in terms of y x and y x. Of course, we know both are equivalent. The more, this is also one dimensional form of Newton's law of viscosity. This also one dimensional form of Newton's law of viscosity, and this also, okay. But this one is very much specific for this case. The most frequently written form is this one, okay. This is the form. Moment you come across one dimensional Newton's law of viscosity, you will come across this form of the equation. Okay. Okay. Now, what it says is the shearing force per unit area, that is the left hand side, is proportional to velocity gradient. Okay. In the first time we said force proportional to area, proportional to velocity, inversely proportional to the distance. All of them are put together in one simple statement saying that the shearing force per unit area proportional to the velocity gradient, and of course that is what the Newton's law of viscosity says. Of course, in the one dimensional form, and we used a word saying that experimentally observed. Okay. When is it valid? This one dimensional Newton's law of viscosity is found to be valid for all gases and all liquids with molecular weight less than 5000. Okay. Let us say simple liquids and all the gases, this is found to be valid. Okay. And that itself is a quite wide range of fluids. Okay. What is the units of viscosity? The left hand side you have force per area, so Newton per meter squared. Right hand side you have velocity gradient, so meter per second by meter, giving you Pascal second. Let us look at some numbers for viscosity to get a rough idea what is the magnitude. At 20 degrees centigrade for air it is roughly about 10 power minus 5 Pascal second. For water it is 10 power minus 3 Pascal second, much more viscous than air. If you take glycerol it is 1 Pascal second, still more viscous. So, in terms of increasing viscosity it is air, water and then glycerol, and the graph shown here represents viscosity as a function of temperature, okay. And for gases it increases, and for liquids it decreases with temperature. Okay. So, viscosity depends on temperature and pressure. Of course, pressure dependency is not so significant, but temperature dependency is significant. So, whenever we look up for value for viscosity, we should be careful about the temperature. Look at the steep decrease in viscosity for liquids. So, we should pay attention to the temperature at which we are taking the viscosity data. Let us look at some examples of the simple 1D Newton's law of viscosity. The first example is the same configuration, flow between two parallel plates. So, two parallel plates are 10 centimeter apart, the bottom plate is stationary, the fluid between the plates is water which has a viscosity of 0.001 Pascal second. Calculate the force per unit area necessary to maintain the top plate in motion at a velocity of 30 centimeters per second. So, very simple application of the one dimensional form of Newton's law of viscosity. You have to keep the top plate moving at 30 centimeter per second. Okay. So, let us write down the Newton's law of viscosity in the differential form. Tau yx is equal to nu dvx by dy. Replace this differential in terms of difference, substitute the values, mu is given as 0.001 and velocity difference is 0.3, and here it is 0 because the bottom plate is stationary. Okay. This velocity is velocity of the fluid here clings to the top plate. So, velocity of the fluid is same as velocity of the plate, so 0.3. Similarly, here the fluid clings to the bottom plate, both their velocities are same, which is 0. So, 0.3 minus 0, what is the distance? It is 0.1 minus 0, okay. And so you get a value of 0.003 Newton per meter squared, that is the force required keep the plate moving at 30 centimeter per second, and this value is constant between the two plates, it does not depend on the distance between the two plates. Now, how do you interpret this? Shear force per unit area required to maintain motion of top plate. So, you have to apply a force on the top plate in the positive x direction, you have to pull the plate, and so force acting on the plate is in the positive x direction 0.003. Okay. Now, when this plate will try to pull the liquid along the positive x direction, at the bottom plate what you have is this fluid will try to pull the plate in the positive x direction. So, shear force per unit area exerted by the fluid on the bottom plate is 0.003, and that is what this positive sign indicates. Okay. At the top, force is exerted by the top plate on the fluid. Okay. So, this plate tries to pull the fluid to the right, force is exerted by the top plate on the fluid in the positive x direction. At the bottom, force is exerted by the fluid on the bottom plate along the positive x direction. So, sign convention is important. In this case, if it is by the fluid, then it will be negative x direction, and if it is on the fluid, it will be in the negative x direction. Okay. Here we are interested in what is the force on the plate, so that is on the positive x direction. Okay. Let us look at another example, a very practical example of measurement of viscosity. Okay. Before even going to the example, I like to explain the significance of the geometry. What is the geometry here? The viscosity of a fluid is to be measured by a viscometer constructed of two 40 centimeter long concentric cylinders. So, we have two cylinders, okay, two concentric cylinders, okay, and that is our configuration. Okay. Now, why are we interested in this configuration? Okay. Now, what I have shown here is similar to the example which I have seen earlier, but here the top plate is stationary, the bottom plate is kept in motion. Okay. Now, this configuration is very simple for two reasons. Number one, the velocity profile is linear, we always like to have some simple velocity profile. The simplest velocity profile is linear velocity profile, and then the shear stress, as we have seen in the previous case, which is depends on the derivative of velocity, is a constant, it does not vary between the two plates. So, one of the simplest configuration is this, the flow between two parallel plates. That is why throughout our discussion we have been taking this example. We have used this to explain the difference between solids and fluids, that is the example we took. Remember, we took this example to illustrate difference between solids and fluids. We also took this example to illustrate the one dimensional form of Newton's law of viscosity. So, in that way, a very nice example for such discussion. But now, if you want to realize this configuration in lab, it is very difficult. Imagine you have a plate here, another plate here, and there is fluid in between, and you are setting the plate in motion. How do you realize this in lab? That is difficult. So, that is why you have a configuration where there are two cylinders and there is fluid between the two cylinders, and you are rotating the inner cylinder, and that is why I took in this case the bottom plate to be set in motion. Now, the fluid set in motion between these two cylinders is analogous to the fluid flow between these two parallel plates. But when is it valid? When is it valid? It is valid when the gap between the two cylinders is very small. When it is very small, then you can ignore the curvature and take it that to be equivalent to the flow between the two parallel plates, and you use this arrangement for measurement of viscosity. And when you make such measurements, the gap is very small, so that you can assume the velocity profile to be linear, and that is what is shown here. The velocity profiles are shown to be linear here. When is it valid? When the gap between the two cylinders is very less. Okay. So, now let us continue the example. The viscosity of a fluid is to be measured by a viscometer. Viscometer is instrument used to measure viscosity. Okay. See, actual viscometer can have different configuration, but the principle is this: constructed of two 40 centimeter long concentric cylinders. The outer diameter of the inner cylinder is 12 centimeter, okay, and the gap between the two cylinders is 0.15 centimeter. Look at the value, 0.15 centimeter is a gap, but the diameter is 12 centimeter. Okay. The inner cylinder is rotated at 300 rpm, and then you are measuring the torque, which is 2 Newton meter. So, use a torque meter to measure the torque. Determine the viscosity of the fluid. A very practical example which illustrates the use of one dimensional form of Newton's law of viscosity. More importantly, we have discussed how to realize this flow in a laboratory by having two coaxial cylinders. Okay. First step, what we should do is check really whether the gap is very small. How do you do that? You divide the gap with the radius to find out that the value is in this case 0.15 by 6, which gives us 0.025, which is less than 1. So, we can conclude that the curvature effects are negligible. Then only we can apply the simple one dimensional Newton's law of viscosity. Okay. Velocity profile can be approximated to be linear, that is a conclusion, because the curvature effects are negligible. Okay. So, now let us apply the Newton's law of viscosity, first in differential form, and then we have written in terms of difference. So, let us put in terms of words, becomes easier to proceed further. The shear stress, that is the left hand side, is equal to mu into the velocity difference by the gap. Okay. Now, we are measuring torque, we have to find out viscosity. So, what we are going to do now is find a relationship between torque and then viscosity. We are proceeding towards that. Okay. So, let us write an expression for torque. What is torque? It is force into the perpendicular distance. What is force? The stress into the surface area. So, torque is shear stress into surface area into the perpendicular distance. We have related shear stress to the velocity difference in the previous equation. So, let us substitute that equation. Shear stress is equal to mu into velocity difference by the gap. When I say gap, the distance between the two cylinders, multiplied by surface area multiplied by perpendicular distance. Okay. So, let us continue. The same expression is written here. Okay. Now, when I say velocity difference, the velocity here, the velocity difference between this point and this point. Okay. The inner cylinder is rotating, outer cylinder is stationary. So, velocity there is 0. Whenever we say velocity, we mean the linear velocity. So, how do we convert the angular velocity to linear velocity? Multiply angular velocity with the radius omega into r, and what is omega? Express that in terms of the rate of rotation. So, it is 2 pi n and then of course r. So, linear velocity is omega into r, omega is 2 pi n. So, linear velocity is 2 pi n r. Okay. So, let us substitute this. Torque is denoted by capital T here, the viscosity mu, which is yet to be determined. Velocity difference is omega r minus 0, inner cylinder omega r, outer cylinder it is 0, the gap is h. Okay. And what is surface area? Surface area of the cylinder is 2 pi r L. What is the perpendicular distance? It is r. Okay. If you multiply these terms you will get this expression and substitute for omega as 2 pi n, okay, and you will get this expression. So, we have related torque and viscosity. So, let us rewrite this expression for viscosity, because we have to find out the value of viscosity. So, mu is given by this expression, and so all the values are known. Torque is measured, h is a gap between the two cylinders, which is 0.15 centimeter, r the radius is 6 centimeter, n the speed of rotation is 300 rpm, we have to substitute as rps. So, 5 rps, L is 40 centimeter, substitute all in terms of SI units, okay, and then if you evaluate you will get 0.176 Pascal second. For water it is 0.001, which means you really have a viscous liquid between the two cylinders.